Welcome to this explainer. I'm absolutely thrilled to have you here today. We are about to explore some of the most violent, energetic, and just mind-boggling events in the entire universe. But here's the ultimate cosmic catch. These events, they are completely 100% invisible to traditional telescopes. We're talking about the physics of black hole mergers. We're going to look at what happens when the fabric of the universe itself is stretched, squeezed, and rippled by just unimaginable gravity.
Which brings us to a massive question right off the bat. How do you see the invisible? Okay, let's dive into this. This right here is the central paradox of studying black holes. If a cosmic object is defined by the absolute fact that it swallows all light and emits none whatsoever, how on Earth, or actually scratch that, how in space, can we possibly study it? It sounds like an impossible riddle, right?
Well, to solve this cosmic mystery, we first need to understand what we're dealing with. Section 1. The invisible becomes visible. And it all starts here, with the event horizon. Now, this isn't a physical surface like the crust of a planet. It's a boundary of absolute no return. Once anything, a star, a planet, or even a beam of light crosses this specific threshold, its fate is sealed forever. The gravity is so overwhelmingly strong that the escape velocity actually exceeds the speed of light. And because light cannot escape this boundary, direct visual observation is strictly impossible. No way around it.
Looking at the features of the void, a typical black hole forms at the end of a massive star's life cycle, basically when it collapses under its own immense gravity. At the very center lies the singularity, a point of infinite density where, honestly, our current understanding of physics practically breaks down. And while we can't see the black hole itself, we often see the accretion disk, this superheated glowing ring of matter swirling around it, just waiting to be consumed. Because the singularity traps light, we have to look for clues in the surrounding space-time to even know the black hole is there.
Now, take that concept of an impossibly dense object and imagine two of them finding each other in the dark. Section 2. When black holes collide. Let's move to and see how this builds across the three main phases of collision. First up, we have the inspiral phase. The two black holes orbit each other, gradually losing energy and shrinking their orbit over time. As they get closer, they spin faster and faster. Then comes the merger phase, an intensely violent collision where the two entities just violently smash together to become one single larger black hole. Finally, we have the ringdown. Just like a bell that's been violently struck with a hammer, the newly formed black hole vibrates, emitting final waves as it settles into a stable, perfectly symmetric shape.
To truly grasp the scale of that merger phase, consider this number: 3 solar masses. In the very first black hole collision we ever detected, the final black hole was slightly lighter than the sum of the two original ones. So where did that missing mass go? Well, according to Einstein's famous equation, E equals mc squared, that missing mass, which is equivalent to the mass of 3 of our suns, was converted entirely into pure energy in just a fraction of a second. For a brief moment, that single collision released more power than all the radiant stars in the observable universe combined. Just let that sink in.
But wait, if all that unimaginable energy can't escape as light, where exactly does it go? Section 3. Ripples across spacetime.
The answer lies in gravitational waves. These are literal ripples in the very fabric of spacetime itself. They're caused by accelerating massive objects, like our spiraling black holes, and they travel outward at the exact speed of light. It's absolutely crucial to understand that these waves aren't particles traveling through space. They are distortions of space. It's like dropping a bowling ball onto a trampoline. The fabric of the trampoline stretches and ripples outward. Gravitational waves are the universe's ultimate messenger.
When these waves finally reach us, they arrive with a very specific, recognizable pattern, known as the chirp. As the black holes spiral closer and closer together during that first phase we talked about, the frequency and amplitude of the gravitational waves increase rapidly. They get faster and stronger, peaking at the exact moment of the merger, and then boom, abruptly ending. If you translate this wave frequency into sound, it literally sounds like a bird's chirp. It's a low pitch that rapidly sweeps up to a high pitch and abruptly stops. We can actually hear the collision.
So we know these waves carry the energy of the collision, but how do you actually catch a signal from an invisible collision? Section 4. Catching the cosmic wave. Enter LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO is the world's most sensitive gravitational wave detector. To catch a cosmic ripple, scientists had to build a machine on a truly massive scale. LIGO consists of two massive vacuum tubes arranged in an L shape, and each of these arms is exactly 4 kilometers long. Down these massive arms, incredibly precise lasers are fired to measure distance. Now, what's really interesting about this slide is the staggering contrast in scale here. You've got a detector that is 4 kilometers wide, but it's looking for a shift in distance smaller than the width of a single proton. When a gravitational wave passes through Earth, it literally stretches space in one direction and squeezes it in another. LIGO's lasers detect this minute, microscopic change in the interference pattern of the light. It's kind of like measuring the distance to the nearest star system to the accuracy of a human hair. Just unbelievable precision.
And in 2015, this miraculous engineering paid off with a historic discovery known as GW 150914. Just look at the sheer scale of these stats. This was the very first direct detection of gravitational waves in human history. The signal we caught had been traveling for 1.3 billion years. Two black holes, one roughly 36 times the mass of the Sun and the other 29 times, merged to form a 62 solar mass behemoth. In a single, awe-inspiring fraction of a second, we confirmed the existence of binary black hole mergers and directly proved the theory Albert Einstein proposed a whole century earlier. The implications of that 2015 detection literally changed the course of science forever. Section 5. Listening to the universe.
And this brilliantly illustrates the astronomy paradigm shift we're currently living through. You see, for all of human history, astronomy has been all about looking. Traditional astronomy relied on capturing light and electromagnetic signals. If an event didn't emit light, well, we couldn't see it. But now we have gravitational wave astronomy. We're no longer just looking at the universe, we are actively listening to it. We're detecting the physical distortions in the fabric of reality itself.
Since that first discovery, our cosmic catalog has been expanding rapidly. We detected GW 1512-6 later that same year, which gave us a longer, roughly 1-second signal. By 2017, we added a third detector in Italy called Virgo, allowing us to triangulate and pinpoint exactly where these collisions happen. We've even found massive mergers of black holes over 100 solar masses. These are sitting right in a mass gap where scientists previously thought black holes shouldn't even exist. This suggests black holes might actually be merging multiple times, growing larger and larger, like cosmic snowballs.
The timeline of this journey of discovery is just staggering. It started with pure math and theory on Einstein's chalkboard way back in 1916. It took 99 years of technological advancement for LIGO to make the first physical detection in 2015. And the future? Oh, it's incredibly bright. We're currently developing LISA, a space-based detector that will actually orbit the Sun and detect the slow, rumbling mergers of supermassive black holes from the very early universe.
So the crucial point is this. Why does all of this actually matter to us? Well, for one, it allows us to test extreme physics and gravity in conditions we could never, ever replicate on Earth. It helps us classify and truly understand how black holes form. It ushers in this new era of multi-messenger astronomy, where we can combine gravitational waves, light, and neutrinos to get a complete picture of cosmic events. Ultimately, it turns these violent cosmic collisions into natural laboratories that help us answer fundamental questions about space, time, and the very origin of our universe.
We've really just begun to tap into this new cosmic sense. We've gone from staring blindly at the dark patches of the sky to actually hearing the monumental crashes of the universe's heaviest titans. I'll leave you with this thought to ponder as we wrap up this explainer. If the invisible universe is this loud, what other secrets are waiting to be heard? Keep wondering, keep listening, and thank you so much for exploring space-time with me today.